There is a particular geometric form known as the frustum of a cone. If we were to take a cone with a circular base, as cones do, and if we were to cut the tip off of the cone, what we would be left with is known as the frustum of a cone. Particularly odd word. Not counting the circular top and the circular base, the surface area of that slanted portion that goes all the way around is what is produced for the surface area of a solid of revolution. For example, if we were to take a portion of a curve and as we do, we partition this interval. On any given partition, we know from talking about arc length that there is a diagonal line segment that connects those 2 points. Upon revolving this about the x-axis, this would form a frustum of a cone because it would have a circular face here, and it would have a circular face at the bottom. And this outer edge of this would form what is very similar to a disc. But if all we're interested in is the surface area, then what we're interested in is the outer edge. Just the outer edge, not everything that's filling in the middle, just the outer edge of this. And that's not the easiest thing to come up with because this is definitely not the geometric shape that you're used to dealing with. And surface area of a three-dimensional object is similarly something that we're not particularly used to dealing with. As it turns out, though, there is a very particular formula for the frustum, the surface area of the frustum of a cone. The surface area, not counting the circular faces, is given by S is equal to 2 pi r times L, where L is the slant length, the slant height, if you will. R, then, is the average of the 2 radii of the upper circle and the lower circle. So we could call this top radius r sub 1 and this bottom radius r sub 2. And r then is equal to the average of those 2 radii. You might think of it as the radius halfway up that frustum. This is the formula for the surface area. On a sideways cone, a sideways frustum, as is created when we revolve this one line segment around the axis, The slant height is the length of the line segment, which we know to be given by the square root of 1 plus delta y over delta x squared, all under the square root. Oh, excuse me, times delta x. This is our slant height. Our two radii then would be the height of the function at the right endpoint of the interval and the height of the function at the left point of the interval. However, the interesting thing that happens is that as our partitions grow in number, they narrow in width. So the size of the left radius and the size of the right radius approach the same value. Ultimately, as n goes to infinity, r sub 1 and r sub 2 approach the same value. Therefore, r is going to approach 1/2 times 2 times r sub 1, or 2 times r sub 2, whichever you prefer to use, which simply is r sub 1. The idea then is that we can use either the left or the right side because they are essentially going to be the same number. And what that ends up being is simply the height of the function somewhere in the partition. So our radius essentially ends up simply being f of x. What this gives us ultimately then is that the surface area on each partition, the surface area of the ith frustum, is going to be given by 2 pi times f of x sub I times the square root of 1 plus delta y sub I over delta x sub I squared times delta x. Our surface area then is approximated by the sum of all of these frustums and is given exactly by the limit as n goes to infinity of this Riemann sum. Which we know to then be given by the definite integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. So this being based on the line segment on the partition has the same aspect, the square root here, the same aspect as the arc length formula, but because it is not just a one-dimensional measurement, this is now a two-dimensional measurement, we have also the multiplication by f of x, which gives us the radius of the frustum, which is necessary because we do have the rotation then. So we have this slanted line, the length of the slanted line being covered by the square root portion. And then we have the 2 pi r, the 2 pi times f of x, accounting for the circular rotation of that slanted segment. Of course, we need to look at some examples with this. This can, as with all of the previous formulas in this unit, can easily be adapted to be done in terms of y rather than in terms of x, depending on which axis of rotation we are using. For a horizontal axis of rotation, such as the x-axis, we would be integrating with respect to x. For a vertical axis of rotation, such as the y-axis, we would be integrating with respect to y. So let's consider an example. Suppose we take the graph of f of x is equal to x cubed on the interval from 0 to 1. And this is going to be revolved around the x-axis. This would form a three-dimensional structure. If we were looking at it being filled in, we would have to define a fully enclosed region. But in this case, we're only interested in the outer edge of that three-dimensional object. So we really only need the curve that is tracing the outer edge of the shape. So unlike the volume questions, we don't need to define a fully enclosed region. We just need to define a section of a curve that then will get rotated and create the outer surface. So it would help to maybe take a look at this. Of course, x cubed is going to go from 0, 0 up to 1, 1. And it's going to do so in a curving fashion. Now, when this curve then gets rotated about the x-axis, it's going to result in what's going to look like, well, the bell end of a trumpet, basically. It's going to create a three-dimensional shape, or the outer surface of a three-dimensional shape. And each partition on it is going to create that frustum of a cone. So our formula for surface area is S is equal to the integral from a to b of 2 pi times f of x times the square root of 1 plus f prime of x squared dx. So in order for this to work, as with the arc length, we need to make sure that the function is both continuous and differentiable on the interval, which, this being a polynomial function, clearly is both continuous and differentiable. We then need the derivative itself. So we have that f of x is equal to x cubed. And then f prime of x would, of course, be 3x squared. And this is all we need to fill this in. So our surface area is going to be given by the integral from 0 to 1 of 2 pi times x cubed times the square root of 1 plus 3x squared squared dx. The 2 pi is a constant multiple and can be brought in front of the integral, which will certainly make finding the antiderivative a little bit easier to have that out of the way. That leaves us with the x cubed on the outside and a 1 plus 9x to the fourth underneath the radical, which actually is perfect. See, now, if this was just arc length, we wouldn't have the x cubed in front, and we would just have a square root of a sum of squares. But here, we happen to have the x cubed in front, which happens to be part of the variable part of the derivative of 1 plus 9x to the fourth. So this is very well suited to a simple substitution. We will let u equal 1 plus 9x to the fourth, so that du will be equal to 36x cubed dx. Being as there's no factor of 36 in the integrand, there's nothing to take out, so we can divide both sides by 36, and we can substitute in a 1 over 36 along with the du when we substitute out the x cubed and the dx. So our integral is now going to be from x equals 0 to x equals 1. And again, that is an important thing to note, that those limits of integration are x values, not u values. We're going to put in a 1 over 36. Under the radical, we now simply have a u. And then the other half of the x cubed dx substitution, the du itself. We can bring the 1 over 36 out front, where it will become a denominator of 18 underneath the pi. We can rewrite the square root of u as u to the 1/2, of course, and the rest of this should be pretty straightforward. The antiderivative here would become 2/3 u to the 3/2. And again, this is still at x equals 0 and x equals 1. So we either would need to convert the limits of integration to u values, or return the antiderivative to be in terms of x, whichever you prefer, whichever works for you. So when x equals 1, we will have 2/3 times 1 plus 9 times 1 to the fourth, and then that raised to the 3/2, minus pi over 18 times 2/3 times 1 plus 9 times 0 to the fourth, and then that raised to the 3/2. So combining a few steps here, we can simplify the pi over 18 times the 2/3 a little bit to get pi over 27. Then we have 1 to the fourth, which is 1, times 9 is 9. So that entire thing inside the parentheses simply becomes 10 to the 3/2 power. We again have pi over 18 times 2/3, which again is going to simplify as pi over 27. This time, however, because of the 0, we end up with 1 to the 3/2, which of course is simply 1. So if we wish, we could factor a common pi over 27 out of this and be left with 10 to the 3 halves minus 1, which is about as good as we can get it. We could find a decimal equivalent perhaps, but this would be the exact form of the answer. Once again, this can be checked. We can put the integral we established into the calculator and have the calculator evaluate it. The calculator will, of course, give us the decimal equivalent, not the exact form. So to compare them, we would have to evaluate this exact form in the calculator as well and make sure that it gives us the same decimal equivalents. Of course, this is entirely based on the idea that the integral that we created was done correctly. But at least we can check that for the integral that we wrote, we did get the correct result.